So part 3 of the algebraic limit theorem asks us to show that the limit of the product is the product of the limits. Now, this proof will turn out to be a little trickier than the previous two, right? So we'll see why here in a minute. We're going to start the proof the same way we start all the others. Pick an epsilon bigger than 0 and consider the thing that needs to be made less than epsilon. The trouble with what we've got here is that the algebra is not as immediate as it was in the last two cases. So here we're going to employ one of kind of the top two math tricks. The first of those is when you've got some algebra and you can't see what to do, you can multiply it by a clever form of 1 to change the appearance but not the value. Or you can add a clever form of 0 to it, which also changes the appearance but not the value. We're going to use the second of those two tricks. So what we're going to do is inside the absolute value, we're going to subtract Bn times L and add Bn times L, so we don't change the value. And then we still are subtracting Lk. Now, it's not maybe immediately apparent why we would do that, but if we take this out a couple of steps, the first thing we're going to do is split this up into two pieces with a triangle inequality, which is something we've done before. So this is going to look like An Bn minus Bnl plus Bnl minus Lk. And then I've got common factors in each of the two pieces. I can pull out an absolute Bn from the first piece, and from the second piece I can pull out an absolute L. And now we start to see maybe the reason for this trick. Right, what I'm eventually trying to get to is to make this be less than epsilon. And I have to do that by controlling the things I know I can make less than any positive number. A sub n minus L I can make as small as I like because A sub n converges to L. So it seems promising that I can take that small enough to make this first piece be less than epsilon over 2. And then same goes for Bn minus k. Right, I've got Bn minus k times some constant in this case. So if I make Bn minus k small enough, together that piece will be less than epsilon over 2, and then I'll put them together. Well, it's not quite that straightforward in this case, unfortunately, because this b sub n is not a constant. So I first have to get control, so to speak, over this b sub n, so that then I've got a definite way to select my modified epsilon for this piece. Now, there are a couple of ways we can proceed, but it's convenient to use the first result we proved in this section, that because b sub n is a convergent sequence, it's also bounded. So all of these b sub n's, they might bounce around quite a bit, but we know that the absolute value is less than some real number, capital M. So by definition, or sorry, it's by definition bounded, but it's by our theorem from before. Since B is convergent, so since Bn converges, there exists some positive capital M with B sub n less than or equal to capital M for every member of the sequence, for all n's. All right, so making that bound lets me look ahead a little bit and see that what I'm going to be able to do is select this A sub n minus L to be smaller than epsilon over capital M divided by 2. So let's start finishing this up. We've got, by definition, there exists some capital N1 such that if I go that far out in my A sequence, I can make A sub n within epsilon over 2m of L. Note that when I selected the bound, I assumed that it was positive, so I don't have to worry about dividing by 0 there. The 2m is okay. Right? Also, by definition, because the B ends converge, there's an N2 such that N larger than N2 makes Bn within epsilon over 2 times L plus 1. All right, now that one is making use of the same kind of trick that we did in the constant multiple case, where we haven't actually said anything about whether L is 0 or not. I mean, you can separate that into its own case if you want, and this part would then be a little easier. I like to just do it all at once, so as long as I have this L plus 1 in the denominator, right, I can't have 0, and the denominator, right, will be larger than this absolute L by itself. Right, so that allows me, when I put this all together, to do the following. So we're going to let capital N be the larger of our two individual n's, thereby guaranteeing that as long as I'm past capital N in my sequences, both of these things happen at the same time, and that allows me to put them together. All right, N. So if N is bigger than capital N, then what do I get? I get this Bn An minus L plus L Bn minus K. That's going to be less than M times epsilon over 2m plus L epsilon over 2 L plus 1. The m's cancel. The L over L plus 1 piece is smaller than 1, and so that piece is less than epsilon over 2. Epsilon over 2 plus epsilon over 2 means I've arranged for the whole thing. I've arranged for the whole thing to be less than epsilon. Right? So that completes the proof of the third part.